Hi students, in my last video I explained Henry's law and applications of Henry's law as well as Henry's law problems. Right, in today's class, that is lecture number 10, we'll start with vapor pressure. Yeah, but before we'll going to start vapor pressure, in the last video by mistakenly I said applications of Henry's constant, but it is not applications of Henry's constant, it is applications of Henry's law only. You just please make the correction, that's it. Right, now we'll continue vapor pressure. Right, before we'll going to see the vapor pressure, first we have to know about evaporation process. We have to know the definition of evaporation. What is evaporation? Let's discuss now. Evaporation. Right. We'll take one container. In that container, one liquid has taken. In that we'll have liquid molecules. Liquid molecules are present in that container. Now, everywhere we are having molecules. Everywhere we are having that liquid molecules like that. But we are focusing particularly surface area liquid molecules only more. Surface area liquid molecules, we'll observe what happens, we'll see now. Then surface area liquid molecules, if you see, these molecules are having less intermolecular attraction forces. Surface molecules are having less intermolecular attraction forces. Why? If you see the bulk, inside the liquid, suppose if you take this molecule, attraction forces are existed from this side, as well as this side also. All four sides attraction forces are existed. But if you see the surface molecule, from all the directions, from upside attraction forces are not existed. That's why intermolecular attraction forces are less on surface molecules. And the second point is surface molecules are having more kinetic energy. Surface molecules are having a more kinetic energy. Because of these reasons, what happened? Surface molecules will convert into vapors easily. Surface molecules are converting into vapors very easily. This phenomena only called as vaporization. The conversion of liquid into vapors. The conversion of liquid into vapors from its surface area is called as vaporization. And the thing is, vaporization takes place at any temperature below its boiling point, remember. At any temperature, vaporization takes place below its boiling point. Right. Now, our target is vapor pressure. Vapor pressure. Yeah. Before we'll going to see the vapor pressure, one more definition we have to see, that is called condensation. Condensation. Evaporation already known to you. Now we'll see what is condensation. Suppose if it is a closed container, what happens? All liquid molecules are converting into vapor state. All liquid molecules are converting into vapors, and after that vapor molecules, because it is a closed container, vapor molecules again will come back. Vapor molecules are again come back and they will attract by the surface molecule and convert it into liquid. Vapor molecules again converted into liquid. Liquid converted to vapor. Evaporation. Again vapor converted into liquid, that is only called as condensation. Okay, initially what happened? Evaporation takes place. Then after some time what happens? Condensation takes place. Then evaporation, condensation. Then after a certain period of time, an equilibrium is established. An equilibrium is established between a rate of evaporation and a rate of condensation. Therefore, at equilibrium what we can write? Rate of evaporation is equals to rate of condensation. Then this stage is called as equilibrium stage. I'll repeat, at equilibrium stage, rate of evaporation and rate of condensation becomes equal. That stage is of course called as equilibrium stage. Right, now we'll see what is vapor pressure. Right, at equilibrium, remember, at equilibrium, then liquid converted to vapor, of course, vapor converting into liquid. Then in this phenomena, what happens? During the conversion of vapors into liquid, say it is a surface. When vapors are converted into liquid, when vapors are converting into liquid, then these vapors are exerting some pressure. Vapors are exerting some pressure on the liquid surface at equilibrium. That pressure is called as vapor pressure, remember. The pressure exerted by the vapor molecules on the surface of liquid molecules at equilibrium stage is called as vapor pressure. I'll repeat once again. Vapors are converting into liquid. When vapors are converting into liquid, definitely vapors will exert some pressure. Vapors will exert some pressure on the liquid surface at particular state. Which state? At equilibrium stage. That pressure is called as vapor pressure. That's why the pressure exerted by the vapors on the surface of liquid at equilibrium stage is called as vapor pressure. Then here vapor pressure depends on certain factors. What factors? Let's discuss now. Factors on which vapor pressure depends. First factor is temperature, remember. You just guess then. If temperature increases, evaporation increases. If evaporation increases, automatically vapor pressure also increases. That's why temperature and vapor pressure both are directly proportional to each other. When temperature increases, vapor pressure also increases. Second one is nature of liquid. Means whatever the liquid we are taking, its nature also played an important role. How? Means suppose if this liquid is having more intermolecular attraction between the molecules. If liquid is having a more intermolecular attractions between the molecules, definitely rate of evaporation is less. If rate of evaporation is less, automatically vapor pressure also less only. Once again, nature of liquid. If liquid is having more intermolecular attraction forces in them, evaporation is less, automatically vapor pressure is also less only. And next one is boiling point. Generally, less boiling point liquids. Less boiling points liquids are having a high vapor pressure. Less boiling point liquids are having high vapor pressure. These are the factors which influence the vapor pressure. Right. This is the vapor pressure. Next we'll discuss about Raoult's law for solution of. We'll discuss about Raoult's law. I'll give you the heading. Raoult's law for a solution of volatile liquids. Raoult's law for a solution of volatile liquids. Let's see now what this statement will explain. First we have to know what is meant by volatile liquid. Volatility, nothing but easily vaporizing tendency is called volatility. Easily vaporizing, more vaporizable tendency is called as volatile in nature. Right. Raoult's law for a solution of volatile liquids. Okay. Suppose, please try to understand, it is one container. Here one particular liquid, particular component have taken. Say it is a component 1. And it is again another component 2. Sorry. We'll write same size of course. It is a component 2. Component 2. Now what I am doing, of course it is a closed container, it is also closed container only I am taking. Now both the components we are dumping in one big container. We are dumping in one, we are mixing in one big container, big closed container. It is a mixture of component 1 and 2. Mixture of 1 and 2. Let's discuss what happens here. It is a pure component 1. It is a pure component 2. It is a mixture. See, for example, component 1, let it as a solvent. Component 2, let it as a solute, because 2 will be designated with a solute, 1 will be designated with a solvent. Okay, it is a solution, of course. Right. Now, it is a closed container. Then what happened? Here from the surface, vaporization takes place, condensation takes place. During the condensation, what happened? Then those vapor molecules will exert some pressure. That pressure is called as vapor pressure. Vapor pressure of component 1, I am indicating with a P01. Sir, what is meant by naught? Naught is nothing but a purity designated with this naught, 0. P01 means only component 1 exerting pressure is designated with P01. Exactly. Component 2. Here also only component 2 is exerting pressure on its liquid surface. That is called a P02. P0. Naught means pure. No other component here. Come here. It is a mixture. Mixture, of course. In mixture we are having two components. Component 1, component 2, both are present. That's why here component 1 is exerting pressure, component 2 is exerting pressure, 1 exerting, 2 exerting, 1 exerting, 2 exerting, 1, 2, like that. Both the components are exerting pressure. If both the components are exerting pressure, means it is a mixed pressure. That's why here we cannot tell P01, P02, sorry, P0, here we will write P01, P02 we cannot write here because it is not a pure component. It is a mixture. In case of mixture, we have to mention partial pressure with a normal symbol P1, with a normal symbol P2. That is called partial pressure of component 1, partial pressure of component 2. Say it is component 1 pressure, it is component 2 pressure. It is a P1, it is a P2, partial pressure. What is meant by partial pressure? Means in mixture, one component exerting pressure is called partial pressure. In a mixture, one component exerting pressure is called as a partial pressure. That's why here we are showing a P1 and P2. Here we are showing a P1 naught and a P2 naught. See the difference. These two are the pure components. It is a mixture. It is a mixture. Right. Now, according to Raoult's law, what is our heading? Raoult's law for a solution of volatile liquids. It is a solution. Volatile. A is volatile. Component 1 is volatile, component 2 also volatile. That's why component 1 is exerting pressure as well as the component 2 also exerting pressure. Therefore, according to Raoult's law, whatever the partial pressure is there, that partial pressure is directly proportional to its mole fraction. Partial pressure of component 1 as well as partial pressure of component 2 is directly proportional to their corresponding mole fractions. Where? In the mixture. That's why how to define now Raoult's law? How to define Raoult's law means the partial pressure of each component. The partial pressure of each component in the liquid mixture is directly proportional to its mole fraction. Once again, the partial pressure of each component in the liquid mixture. Because the liquid mixture is directly proportional to its mole fraction. This is only called Raoult's law for a solution of volatile liquids. Okay, right. Now we'll extend its formula. How to extend? Let's discuss now. Because we are having two components. One is component 1, component 2. I'll write for component 1. We'll write the P1 directly proportional to x1. Therefore, P1, if I remove proportional to symbol, I can write the constant P1 not x1. P1 not x1. Yeah. Then, for component 2, then P2 directly proportional to x2. Therefore, P2 is equals to P0 to x2 we can write. Okay. But we are taking a mixture, liquid mixture we are taking. That's why we'll use now here Dalton's law will use here. According to Dalton's law, from Dalton's law of partial pressure, okay, now P total is equals to P1 plus P2 according to Dalton's law of partial pressure. Therefore, P total, I'll write that side, I'll write this side here. Yeah. P total is equals to P1 plus P2 according to Dalton's law. Now, we just will substitute those values. That is a P1 not x1 plus P2 not x2. It is nothing but a P total. P total. Yeah. Now, what I am doing, please try to understand, either x1 or x2, then out of those two will convert either this x1 into x2 or x2 into x1. That is your wish. Once again, I'll tell you, x1, x2, out of these two, x1 we have to convert it to x2 or x2 we have to convert it to x1. Any one we have to convert. Then we'll follow our NCERT book. According to our NCERT book, x1 also he has converted into x2. How? Because x1 plus x2 is equals to 1. This is our formula. The sum of mole fractions of all the components is always equals to unit 1, unit E. Therefore, x1 is equals to 1 minus x2. I will dump here. P total is equals to P1 naught 1 minus x2 plus P2 naught x2. Okay, means in place of x1 I substituted 1 minus x2. Okay, therefore P total is equals to P1 naught minus cross multiplying P1 naught x2 plus P2 naught x2. Okay, right. Next, we'll write here remaining derivation part. P total is equals to then P1 naught plus here x2 is there. I'll take x2 as common. X2 if you take common, if you take common, P2 naught minus P1 naught. P2 naught minus P1 naught, we are getting, this is the total pressure formula. Here P2 naught, first we are writing a minus P1 naught, next we are writing a means, here component 2 is highly volatile comparing with the component 1. Component 2 is highly volatile. Because of that reason only, component 2 vapor pressure is more than component 1. Means here component 2 vapor pressure is more than component 1. That's it. Component 2 vapor pressure is more than component 1, like that you have to assume. Okay. According to Dalton's law, total pressure expression we have derived. Or here what I am doing here, x1 has replaced with 1 minus x2. Means I have converted into x2 terms. Or next your job is, what you have to do, x2 you have to replace with 1 minus x1. x2 you have to replace with 1 minus x1, and the entire formula you have to convert in terms of x1 also, doesn't matter. Then this formula has given in the NCERT book, that's why I have written not only this formula, x2 also you can convert it into x1. How? x2 place mein 1 minus x1 if you substitute, you will get entire formula in terms of x1 only. Right. Next, what we have to do? We have to plot the graph between vapor pressure as well as mole fraction. Vapor pressure, mole fraction graph we have to derive. We will see now. Once again, we will write here the formula. Total pressure is equals to, the formula is P1 naught x2 P2 naught minus P1 naught is the formula. This is the formula. Okay, P1 naught is equals to, P total equal to P1 naught plus x2 if you take common, P2 naught minus P1 naught. Now, how to plot graph will discuss now. Right. For plotting a graph purpose, I will take P1 is equals to P1 naught x1. Next, P2 is equals to P2 naught x2. I will write here. Okay. Next, here what I am doing, please try to understand. Here x1 is there. That's why if x1 is equals to 1. If x1, if I substitute with one number, if x1 equal to 1, P1 naught into 1, P1 naught only. Therefore, P1 is equals to P1 naught. This is first point. Or if x1 equal to 0, if I substitute in place of x1, if I substitute 0, then 0 into something 0. Therefore, P1 is equals to 0. We will get this again. You have to remember. Once again, P1 equal to P1 naught x1. This already known to you. Here, what I am doing in place of x1, I have substituted 1. Automatically, P1 equal to P1 naught. Here again, x1 substitute with the 0. P1 equal to 0. Exactly here also same. If x2 equal to 1, if you substitute 1, therefore P2 is equals to P2 naught. If again x2 equal to 0, if you substitute 0 into something, P2 you will get a 0 only. Now what we have to do, based on this information, we have to plot the graph between vapor pressure and mole fraction. Right. We'll write this information here. P1 equal, if x1 equal to 1, then P1 equal to P1 naught. It is one point. And if x1 equal to 0 and P1 equal to 0, next here what I am doing, second point, if x2 equal to 1, P2 equal to P2 naught, again if x2 equal to 0, P2 equal to 0, these points we have to remember. Based on that only we will plot the graph like this. Yeah, please try to understand. Okay, then it is y-axis, it is also y-axis. I have taken at both the places. Say it is x-axis. Now here I am taking a component 1. Component 1 I will write this side. Component 2 I will write this side. On y-axis I have taken a partial pressure. On x-axis I will take a mole fraction. Yeah. Now we'll try to follow graph. See here. Component 1, this side only component 1 is there. If only component 1 is there, x1 equal to 1 and x2 equal to 0. Because only component 1 is there, means component 1 mole fraction is 1 and component 2 mole fraction 0. Because the sum of mole fractions of all components equals to 1. Here only one component is there. One component is there means only x1 equal to 1. And x2 is 0 because component 2 is not there. Automatically, mole fraction of component 2 is 0. Come here. Here only component 2 is there. Component 1 is not there. Therefore, x1 is equals to 0. x2 equal to 1 I will write. We will write clearly. Once again, this side I will write component 1. That's why only x1 equal to 1, x2 equal to 0. This side I'll write component 2. Component 2 means only second component is there, first component is not there. That's why first component mole fraction is 0, second component mole fraction is 1. Right. Now from this formula, what is the conclusion? Conclusion is second component vapor pressure is more than first component. That is very important. From this formula, second component is highly volatile. Its vapor pressure is more than first component. Right. Okay. Now, here only component 1 is there, component 2 is 0. That's what I am doing now. See here, if x1 equal to 1, p1 equal to p1 naught. P1 equal to P1 naught. What is its meaning? Means here if only one component is there, means its partial pressure I am locating here. Say it is a P1 naught. If x1 equal to 0, then pressure is a P1 naught I am locating here. Come here only x2 is there, second component is there, first component is not there. Second component partial pressure I am locating here. Why? Somewhat height, it is somewhat low height, it is somewhat higher height. Why? Because component 2 vapor pressure is more than component 1. Based on that, this we have mentioned somewhat height, this we have to mention somewhat lower height. It is a more height, it is a less height. We'll locate here, of course. Here, why we are writing a P2 naught? Why we are writing a P2 naught? Means x2 equal to 1, then P2 equal to P2 naught. X2 equal to 1, whatever the pressure is there, that pressure I have located here. It is a less height, it is a more height. Why? Because component 2 is more volatile than component 1. Okay, next one. If x1 equal to 1, p1 equal to p1 naught. If x1 equal to 0, p1 equal to 0. Come here, where is x1 equal to 0? This is x1 equal to 0. If x1 equal to 0, then what about p1? P1 is 0. Component 1 partial pressure 0. Component 1 partial pressure 0 means here only, because from bottom to top partial pressure increases. Then here its value 0. That only I have located here. No confusion here, of course. Once again, if x1 equal to 0, partial pressure of component 1 is 0. That's why x1 equal to 0, partial pressure of component 1 is 0. Because here component 1 is not there, only component 2 is there. That's why component 1 partial pressure is a bottom we have taken because 0. Okay? And just will connect these two like this. Once again, we'll get straight line, of course. Straight line is obtained. Then here first, once again, x1. If x1 equal to 1, component 1 partial pressure is P1 naught. That only we have taken. If x1 equal to 1, means only one component is there and its pressure I have located here. It is a P1 naught. And next, if x1 equal to 0, means component 1 is not there, automatically its pressure also 0. That's why x1 equal to 0, means here component 1 is not there. Component 1 is not there, means its pressure is 0. We are locating here, and if you connect, we are getting a straight line. It is completely P1 changing only. P1 changing only. Here P1 equal to P1 naught, here P1 equal to 0. P1 equal to P1 naught, P1 equal to 0 means P1 changing is taking place. Next, come here. If x2 equal to 1, P2 equal to P2 naught, that only we have written. If x2 equal to 1, P2 equal to P2 naught, second component of partial pressure is here. Next, if x2 equal to 0, P2 equal to 0. If x2 equal to 0 means here x2 equal to 0. Means here second component is not there, only first component is there. If second component is not there, means automatically its pressure is 0. Here component 1 is not there, its pressure is 0. Here component 2 is not there, its pressure is 0 here. Again we are connecting these 2 points like this. Of course, straight line should come. Okay, and this is a P2 variation. P2 variation only. If x2 equal to 1, P2 equal to P2 naught. If x2 equal to 0, P2 equal to 0. It is a P1 variation, it is a P2 variation. Now I want a total pressure. These two lines we are connecting. If you connect these two lines, P total is equals to P1 plus P2. That's it. This is about Raoult's law for a solution of volatile components in liquid mixture for this graphical representation. Okay, graphical representation. Please try to understand. Left side I have taken component 1, right side I have taken the component 2. Here a graph has plotted between partial pressure versus mole fraction. It is a y-axis, partial pressure. It is also y-axis, partial pressure only taken. X-axis, mole fraction has taken. Here only component 1, that's why x1 equal to 1, x2 equal to 0. Here only component 2, that's why x2 equal to 1, but x1 equal to 0. And this information, how we have written already known to you. Based on that, if x1 equal to 1, x1 equal to 1 means only one component is there. If only one component is there, automatically its pressure is nothing but a pure component pressure. That's why if only one component is there, its pressure is nothing but its own pressure. That's why we are showing a P1 naught. P1 naught is nothing but a pure component pressure. Because only one component is there, automatically its pressure is a P1 naught. Okay, next one. If x1 is 0, P1 equal to 0. x1 equal to 0 means x1 0 here. x1 0 means one component is not there. If one component is not there means automatically its pressure is 0. Its pressure 0. That's why here pressure is P1 naught, here pressure is 0. We will connect means pressure component. Component 1 pressure variation we are getting, it is P1. Similarly, if x2 equal to 1, x2 equal to 1 means it is x2 equal to 1, means only second component is there. If only second component is there, its pressure we can indicate with a P2 naught. Because only one component is there, we'll write it as P1 naught as well as P2 naught. Okay, right. If only component, second component is there, its pressure is a P2 naught. That's why next if x2 equal to 0, here x2 equal to 0, x2 equal to 0 means the second component is not there here. That's a second component pressure is 0. Here first component pressure 0, here second component pressure 0. That's why again if you connect, you will get a straight line. It is a P2 variation, it is a P1 variation. And I want a total pressure, both P1 and P2 if you add, you will get a total pressure. This is a graphical representation. Okay, no any confusion here, no any confusion. Once again I will write here, P1 is equals to P1 naught x1 and P2 is equals to P2 naught x2. What we are doing here, if x1 equal to 1, if I substitute, meaning is P1 naught into 1, therefore P1 equal to P1 naught. If x1 equal to 0, if you substitute 0, P1 equal to 0. That information only we have written there. Here again, same. If x2 equal to 1, P2 equal to P2 naught. Again if x2 equal to 0, P2 equal to 0. That information only we have written there. From this equation, what is the conclusion? Conclusion is the second component pressure is more than first component. That's why second component maximum pressure is here. First component maximum pressure is here. It is more heighted. It is less heighted. This is about a graphical representation. Next, we will discuss about Dalton's law of partial pressure for gaseous components. Dalton's law of partial pressure for gaseous components. Gaseous components. Dalton's law of partial pressure for gaseous components, right? For gaseous components already known to you, partial pressure is equals to mole fraction into total pressure is the formula. Partial pressure is equals to mole fraction into total pressure. For a particularly gaseous components, remember, here what I am doing, mole fraction of gaseous components represented with Y symbol, remember. Previously mole fraction we have represented with X symbol. Now mole fraction we are representing with Y symbol because here components are gaseous components. Therefore same, component 1, partial pressure of component 1 is equals to mole fraction of component 1 is Y1 into total pressure P total is formula. Mole fraction into total pressure. What is Y1? Component 1 mole fraction in the vapor state or in the gaseous state. Exactly. Second component P2, Y2 into P total. Because based on these formulas also we are having the problems. Now we'll solve one or two questions based on all these formulas. Okay? We'll see the question now. Right. Yeah, before we'll going to see the problem, the same graph once again we'll discuss. I'll explain in another different manner like this. See here only component 1 is there, component 2 0. Here only component 2 is there, component 1 0. Then only component 1 is there means its pressure is, it's a single component pressure is P1 naught. When we are going from left to right, when we are going from left to right, what happened? Component 1 becomes 0. Component 1 becomes 0. Component 1 is vanishing. Automatically its pressure also decreasing only. Once again, left to right if you observe, here component 1 is there, here component 1 0. Component 1 vanishing from left to right. That's why its pressure also decreasing only. Exactly. Here only component 2 is there, here component 2 0. That's why if only component 2 is there, its pressure is highest. Then again we are coming from right side to left side. Right side to left side, what happens? Component 2 is vanishing. Component 2 is vanishing. Automatically its pressure also decreases and becomes 0. That's it. Like this also we can explain this graph. Okay, because left side, here only component 1 is there, its pressure is maximum. Then here component 1 is 0. Automatically what happened? Pressure is decreasing and becomes 0. And right side, only component 2 is there, its pressure is maximum, P2 naught. And we are coming from left side, here component 2 is 0. Component 2 becomes 0, automatically its pressure also decreasing and becomes 0. That's it. Like this also we can explain the graph. Right now we'll see the question based on these formulas. Right. Yeah, we'll understand the question first of all. The vapor pressure of pure benzene and toluene. Benzene and toluene vapor pressures at 27 degrees centigrade are, one is 25 millimeters of mercury, sorry, one is 75 millimeters of mercury, one is 25 millimeters of mercury. It is a benzene vapor pressure, it is a toluene vapor pressure, and 2.34 grams of 2.34 grams of benzene mass has given, 64.4 grams of toluene mass also given. Then what he is asking? Partial vapor pressure of each component. Partial vapor pressure means P of benzene and P of toluene, as well as P total vapor pressure means partial pressure of benzene, partial pressure of toluene. He is asking in the first question. In the second question, mole fraction of each component in the vapor phase. Mole fraction of each component in the vapor phase means mole fraction in the vapor phase we are designating it the Y symbol, means Y of benzene and Y of toluene he is asking. Right. We'll see both the questions now. First what we have to do? partial pressure of benzene, partial pressure of toluene we have to calculate. Partial pressure of benzene formula is P naught B into XB is the formula. PB equal to P naught B XB. Then P naught B is nothing but that is a pure benzene vapor pressure. Pure benzene vapor pressure already given. Pure benzene vapor pressure is a 75. That's why here we will substitute 75. No doubt. XB. Benzene mole fraction we have to calculate. How to calculate benzene mole fraction? Number of moles of benzene by total moles. That's why first our job is we will calculate benzene mole fraction as well as toluene mole fraction we will calculate. After that we will see this question. Benzene mole fraction, toluene mole fraction we will calculate. Okay. Then where we will write means solution I will write here only. Then a mole fraction of benzene, that is a number of moles of benzene by total moles, number of moles of benzene plus number of moles of toluene. But in the question unfortunately number of moles of benzene and toluene has not given. Instead of moles has given mass. That is 2.34 grams of benzene mass and 64.4 grams of toluene mass given. With the help of mass we can calculate moles easily. That's why moles nothing but mass by molar mass. Benzene mass by molar mass. I'll write here only. Mole fraction of benzene is equals to number of moles of benzene means mass by molar mass. Mass of benzene how much? 2.34 divided by benzene molar mass C6H6 that is a 78 divided by again benzene moles 2.34 divided by 78 plus toluene mass 64.4 divided by toluene molar mass is 92. If you simplify, you will get a mole fraction of benzene is obtained. Mole fraction of benzene, how much you will get? 0.041. 0.041 is a mole fraction of benzene. Now I want a mole fraction of toluene also. Mole fraction of toluene, how you will get? Directly will get. That is mole fraction of benzene plus mole fraction of toluene is equals to 1. Therefore, mole fraction of toluene equals to 1 minus mole fraction of benzene. That is nothing but 1 minus 0.041. If you subtract toluene mole fraction, you will get 0.958. 0.958 is the toluene mole fraction. Now, what is our job? Partial pressure of each component. Partial pressure of each component we have to calculate. Means benzene partial pressure as well as toluene partial pressure, both we are calculating here. Question 1. First question we have started now. Partial pressure of benzene means partial pressure of benzene is equals to P naught benzene into mole fraction of benzene. P naught benzene, how much they have given then? 75. P naught benzene has given of course 75 into mole fraction of benzene. Just now we have calculated 0.041. If you multiply, you will get a partial pressure of benzene, that is a 3.07. 3.07 units, same units, millimeters of mercury is obtained. This is only partial pressure of benzene, and is asking each component means partial pressure of toluene also we have to calculate. P naught toluene into mole fraction of toluene. P naught toluene, it is a 75, now it is a 25. 25 into mole fraction of toluene 0.958. If you multiply, partial pressure of toluene is obtained 23.9 millimeters of mercury. Of course, first question not completed, is asking a total vapor pressure of the solution, also asking a total vapor pressure. What we have to do? Benzene partial pressure, toluene partial pressure. Benzene partial pressure, toluene partial pressure. Just we'll add, we'll get a total partial pressure. We'll write here P total is equals to Okay, now P benzene plus P toluene. That is nothing but 3.07 plus 23.9. If you add, you will get 27.02 millimeters of mercury. Just now we have completed question number, first question here. It is a partial pressure of benzene, partial pressure of toluene. It is a total pressure. The sum of both the components, you will get total pressure. Second, mole fraction of each component in the vapor phase. Means Y benzene, Y toluene, we have to calculate. Y is nothing but mole fraction in vapor phase symbol. We will write the formula for second question purpose. That is a partial pressure of benzene is equals to mole fraction of benzene into total pressure is the formula. Now he is asking each component Y of benzene, mole fraction of benzene in the vapor phase equals to partial pressure of benzene divided by P total. Partial pressure of benzene, how much already calculated? 3.07 divided by total pressure 27.02. If you simplify, you will get 0.13 something you will get. Exactly, not completed. Next, what we have to calculate? Same, partial pressure of toluene is equals to mole fraction of toluene into total pressure P total. Again I want a mole fraction of toluene in vapor phase equals to P toluene divided by P total. Partial pressure of toluene is already there. How much? 23.9. 23.9 divided by total pressure 27.02. Again, if you do the calculation, you will get 0.886. 0.886 are the answers. This is mole fraction of benzene in the vapor phase. It is a mole fraction of toluene in the vapor phase, because mole fraction in the vapor phase will be designated with the Y symbol. Please don't forget, remember. Now next what I am doing, same type of question I will give you as homework. Okay. Yeah, quite a similar question I have given here. Vapor pressure of chloroform and dichloromethane at 298 kelvins are 200 millimeters and 415 millimeters of mercury. Chloroform vapor pressure as well as dichloromethane vapor pressure has given. And what is asking? Number 1, calculate vapor pressure of solution. Vapor pressure of complete solution only is asking. Prepared by mixing 25.5 grams of chloroform. Again, chloroform mass has given, and 40 grams of dichloromethane. Dichloromethane mass also has given, of course, at 298 kelvins. Second question, same type, mole fraction of each component in the vapor phase. Each means one is a chloroform, one is a dichloromethane. Yeah. Now, here again, vapor pressure of solution we need. Vapor pressure of solution means first partial vapor pressures of both the components we have to calculate. Partial vapor pressure of chloroform we have to calculate. Partial vapor pressure of dichloromethane we have to calculate. For that purpose, we need mole fraction. Here I have calculated. I have given answer. Mole fraction of chloroform is this much. Mole fraction of dichloromethane is this much. But what I did here, total vapor pressure given. Partial vapor pressure of chloroform, partial vapor pressure of dichloromethane have not given in here. Then you have to calculate. Then both if you add, you have to get this much. If you get this much, your answers are correct. Otherwise, your answers are wrong, of course. And second question, mole fraction of each component in the vapor phase. Mole fraction in the vapor phase will be designated with the Y. That's why Y chloroform value 0.18. Y dichloromethane value 0.82. These are the answers. It's quite similar to our previous question only. You have to once again glance, you have to once again watch previous question and its solution. Then you have to solve this question. Okay? Right. Next, we'll discuss one more different as well as very important for a competitive examination purpose. One question we'll see now. Different question, of course. Question is like this. Find out vapor pressure of pure benzene and pure toluene in the solution and total vapor pressure P total is equals to 100 plus 60 XB. 100 plus 60 XB has given then is asking a mole fraction. Okay, right, that's it. This is the question, and what he is asking means in the question, please we'll try to understand. Find out the vapor pressure of pure benzene, nothing but P naught benzene is asking. P naught benzene. P naught is nothing but pure benzene and pure toluene. P naught toluene he is asking. For that purpose, one information he has given. P total equal to 100 plus 60 XB. Right, we'll see the solution. We'll see the solution part. That is, we'll write here. P total is equals to, according to Raoult's law, P naught benzene into X benzene plus P naught toluene into X toluene. Just like a P total equal to P1 naught X1 plus P2 naught X2. Based on this I have written here. Okay, or we'll write symbols every time. No need to write benzene. P naught benzene X benzene plus P naught toluene X toluene. This is T. We'll write, of course, P total it is. No confusion. It is a toluene, it is total. Toluene total. Right. Now, here XB, B for here benzene has given. B for benzene, we'll write XB is mole fraction of benzene. So what I am doing now, in given statement benzene mole fraction is showing, let's say here also wherever a toluene mole fraction is there, that toluene mole fraction also I will convert into benzene mole fraction like this. P naught B XB plus P naught T, instead of XT I will write 1 minus XB, because the sum of mole fractions of all the components is equals to 1. Based on that, mole fraction of toluene is nothing but 1 minus mole fraction of benzene. We can write P naught benzene XB plus, will multiply P naught toluene minus P naught toluene into 1, P naught toluene minus P naught toluene into XB. Next, what I am doing now, here we'll do one thing, XB, P naught toluene will write first. P total is equals to P naught toluene plus here XB is there, here also XB is there. We'll take common, XB will take as common. If you take common, what we will get? P naught B minus P naught benzene minus P naught toluene will get. P naught benzene minus P naught toluene. Same equation I have written here. This P naught toluene I have written first. because here a mole fraction of benzene is there, here also mole fraction of benzene is there. Mole fraction of benzene, if you take common, first we will write a mole fraction of partial pressure of benzene minus partial pressure of toluene, that only I have written. Now both equations we have to compare. We have to compare both equations. That is P total is equals to 100 plus XB, and in place of this we are having 60. What is asking? Find out the vapor pressure of pure benzene and toluene is asking. Means P naught benzene, P naught toluene. Here already when we are comparing to each other, P naught toluene value is visible. Therefore P naught toluene is equals to 100. Answer obtained. P naught toluene value 100, no doubt. Now next what we are doing? XB. P naught benzene minus P naught toluene is 60. From that we have to calculate P naught benzene value. Therefore, P naught benzene minus P naught toluene equal to 60. Because both we are comparing the equations. Okay, when you are comparing in place of P naught toluene 100 is there, that directly we will write the value. But P naught B minus P naught T, P naught benzene minus P naught toluene value 60. From that we will do like this. I want a P naught benzene minus P naught T will shift that side. Minus P naught means 60 plus P naught T. Already P naught T value is 100. 60 plus 100. Therefore, P naught B is equal to 60 plus 100. That is nothing but 160. Both answers we have calculated. That's it. Okay, once again, this is the given value, given statement. And what we are doing now, here are two components given. One is a benzene and toluene. According to Raoult's law, total equal to P naught benzene and its mole fraction, P naught benzene, X benzene, P naught toluene, X toluene I have written. And next, in the given statement, benzene only appearing. That's why here this toluene also I changed as benzene. That's why we have substituted 1 minus benzene. And if you simplify, we are getting one equation. This equation and this equation, this one, when you are comparing to each other, then in place of P naught toluene 100 we are getting, and in place of P naught B minus P naught T we are getting 60. From that P naught benzene has calculated. And we can also, we can solve like this lengthy method, or we are having even a short trick also for this type of questions, remember. Now I will give you short trick how to calculate. You will write here same equation, or another method. P total is equals to 100 plus 60x benzene. 60x benzene. Right. Now I want vapor pressure of pure benzene. Vapor pressure of pure benzene purpose. Pure benzene means only benzene will be there. Only benzene will be there, toluene is not there. That's why in that case we will write XB equal to 1, XB equal to 1, XB equal to 1, as well as X toluene equal to 0 we can substitute. Once again, I want pure benzene vapor pressure. Pure benzene means only benzene mole fraction we have to write as 1. Toluene mole fraction is 0. That's why this one will substitute here. Therefore, we will get P total is equals to 100 plus 60 into 1. That is equal to, because the mole fraction of benzene we have substituted. Mole fraction of benzene only we have substituted, means the toluene is not there. Toluene nahi hai either, no toluene. That's why total pressure is nothing but P naught benzene only. Because no toluene here, total pressure becomes that is a P naught benzene only. Therefore 100 plus 60, 160, that is a P naught benzene. P naught benzene is 160 already. P naught benzene we have calculated as 160. See here directly we are getting. Once again, this is given information. That is given information. Okay. Next, what we are doing now? Our target is pure benzene vapor pressure. Pure benzene vapor pressure means only benzene component is there. Let's say only benzene component mole fraction is 1. Toluene will be 0. No toluene. Let's say whatever the value is there, if I substitute there, then 160 we are getting. Of course, it is a P total. But We have substituted xb equal to 1. xb equal to 1 we have substituted means only benzene we are taking into consideration. Toluene is not there. That's why total becomes only benzene vapor pressure. Therefore 160. Next I want only toluene vapor pressure. Only toluene vapor pressure. Only toluene vapor pressure means x toluene equal to 1 and x benzene equal to 0. Benzene is not there. X toluene equal to 1, x benzene, mole fraction of toluene is 1, mole fraction of benzene is 0. In this formula only mole fraction of benzene is there. That's why in place of mole fraction of benzene I'll substitute 0. Therefore P total equal to 100 plus 60 into 0. Why substitute 0? Why substitute 0 means because we are calculating only toluene partial pressure. Toluene pressure we are calculating. Mole fraction of toluene is 1, mole fraction of benzene is 0. Substitute here, then it is equals to, anyhow benzene mole fraction we have substituted 0 means whatever the pressure we are getting, that is a toluene only. This part 0. Therefore 100 is nothing but P naught toluene. Here also 100 only we are getting. P naught toluene value 100. Very simple. It is a short trick method. For a competitive examinations purpose we have to use like this. First whatever the equation has given you have to write. Now he is asking a pure benzene pressure as well as pure toluene pressure. Here pure benzene pressure purpose xb I have substituted 1. If you substitute there you will get only benzene vapor pressure. Next I want a pure toluene vapor pressure. Pure toluene vapor pressure purpose mole fraction of toluene is 1 but mole fraction of benzene is 0. That's why that 0 if you substitute we will get only toluene vapor pressure. Total becomes a toluene. That's it. This is about short trick method. Here one more question I'll give you, that is homework to you. Homework question I'll give you. Same model you have to solve. No twist here. Question is like this. Homework of course. Mixture of volatile components A and B. Previous case was benzene toluene, here A and B, that's it. A and B has total vapor pressure, or we can write a P total is equals to 254 minus 119 XA, mole fraction of A component, where XA is mole fraction of A of course. Then here find PA naught question mark. Of course PA naught and PB naught also will find. Okay, I'll give you answers. You just try them. Here PA naught is equals to 135 and PB naught is equals to 254 are the answers. It's a quite a similar model only. This type of questions are important for especially competitive examinations purpose. Okay, this type of questions of course till now not asked in the theory examinations, used for important for competitive examination purposes only. Right. Next we'll have till now we have learned Raoult's law of solution of volatile components. Raoult's law of a solution which contains volatile liquids. Raoult's law we have learned. Next one more Raoult's law we have to learn. Raoult's law of a solution contains non-volatile solute. In previous case if you take, here two components are there, both are volatile nature only. Its a derivation, its a definition, everything we have learned. Now one more Raoult law we have to discuss. There one into two components are there, but only one is volatile and other one is non-volatile. Only one is volatile and other one is non-volatile. In that case, how to define Raoult's law, how to derive its expression, that Raoult's law actually will discuss in colligative properties, not now, remember, because this concept will learn in colligative properties, that will discuss in our next classes. Now we'll start ideal and non-ideal solutions. We'll start now ideal and non-ideal solutions. Ideal and non-ideal solutions. Here we are having Raoult's law, two statements. One Raoult law already we have completed, and another type of Raoult's law will learn at colligative properties, not now. Right? We'll discuss now what are ideal solutions and what are non-ideal solutions. First I'll explain about ideal solutions. In first year states of matter lesson, we have learned ideal gas equation. Exactly, we have to learn here ideal solution. Then we'll see the characteristic features of ideal solutions. What are the characteristics of ideal solutions? Means first point, ideal solutions are the solution which obeys Raoult's law, at all temperature and concentration is called as Raoult's law. I'll repeat. Sorry, is called as ideal solution. Ideal solution means a solution which obeys Raoult's law at all temperature and concentration is called as Raoult's law. Sir, what is the meaning of this statement? Which obeys Raoult's law? What is the meaning of which obeys Raoult's law? Means, see here. Say for example, P01 is equals to P0 x1 and P2 equal to P1 equal to P01 x1, P2 equal to P02 x2. Yes or no? Then I want a total pressure. P total equal to P10 x1 plus P20 x2. Then what is meant by obeying of Raoult's law means, now what I am doing on pressure of the solution, calculated experimentally. Here pressure of the solution calculated from Raoult's law. Okay, now see, one solution is there and its pressure has calculated experimentally with a manometer, etc., etc. And same solution pressure also calculated with the help of Raoult's law. And in this case, if both values are getting same, then we can say that that solution is obeying Raoult's law. Experimentally obtained pressure from Raoult's law obtained pressure, if they are same, then we can say that it is obeying Raoult's law. The solution is obeying Raoult's law. Otherwise, it is not considered as obeying. Right. Next point is second point. Ideal solutions characteristics we are discussing. What are the characteristics of ideal solutions? Means suppose we are taking two components. It is one container, please try to follow, and it is another container, and it is another container. Here one liquid have taken, here another liquid has taken. Both the liquids are dumped here. It is a liquid mixture. It is a liquid 1, component 1, it is component 2, it is of course a mixture. Now, what are the characteristics of ideal solutions? Means, here in component 1, between particles will have some attraction forces, that is called as 1-1 attraction force. Between one molecule to other molecule, some attraction forces are existed. Here also between one molecule to other molecule, some attraction forces are existed, that is called 2-2 attraction forces. Okay, 2 is nothing but component 2. Between two molecules some attraction forces existed. Here also between two molecules some attraction forces existed. Now what I am doing, both the components have dumped in one big container. Now what happened here, we will get 1, 2, means this bond is breaking, this bond is breaking, this 1 and 2 will be connected, this 1 and 2 will be connected, 1, 2, 1, 2 bond formation is taking place. Now what is the characteristic feature means, then these two are before mixing, it is after mixing. Before mixing attraction forces must and should be equals to after mixing attraction forces, means 1 1 1 1 and 2 2 attraction forces must and should be equals to 1 2 attraction forces. This is one of the characteristic feature of ideal solution. Remember, the solution which obeys Raoult's law at all temperature and concentration. Second point is before mixing attraction forces as well as after mixing attraction forces should be same. 1 1 1 1 attraction force and 2 2 2 2 attraction force must and should similar to 1 and 2 attraction force. And the next characteristic feature is see, it is a component 1 and a component 2. Say for example component 1 volume is 20 milliliters. Component 2 volume is 30 milliliters. Before mixing, what is the total volume? 30 plus 20, 50. After mixing also, total volume should be 50 only. I'll repeat. Before mixing volume, after mixing volume should be same. There is nothing but delta V mixture is equals to 0. Delta V is nothing but V2 minus V1. V2 is nothing but final volume. Otherwise, Vf we can write. Final volume. Otherwise, V mixture we can write. V mixture minus V components. Okay. Then a mixture volume is 50. Components together also 50 only. That's why no difference. Both the components, before mixture volume, after mixture volume, quite similar. That's why for ideal solutions delta V mixture should be 0. And the next characteristic feature is delta H mixture is also 0. Sir, what is the meant by delta H mixture? Very simple. Here what happened? Here component 1 1 attraction forces are there. Component 2 2 attraction forces are there. Yes or no? Now both has to mix and mixture has to form. For that purpose the existing bond should break. Here we need some amount of energy. Here also existing bond should break. Here also we need some amount of energy. And here bond is forming. After formation of the bond, the amount of energy releasing. See the difference. Here amount of energy required, here amount of energy required, here amount of energy released. Because here bonds are breaking, here bond is making. Before mixing bonds are breaking, after mixing bond is forming. That's why what is meant by delta H mixture means, then here breaking purpose some like 50 kilojoules of energy is required. Here breaking purpose some 60 kilojoules of energy is required. Just imagine. Total 60 plus 50, 110. Means after formation of a new molecule, here same 110 kilojoules of energy only releases. Before mixing energy, after mixing energy should be similar. That is only called as delta H mixture 0. Here also same. H mixture minus H components are same. Because here bonds are breaking. Here bond is making. After bond formation, amount of energy released. For breaking purpose, amount of energy required. Here required energy must and should be equals to released energy. These are the characteristic features of ideal solution. Once again, what our ideal solution is? A solution which obeys Raoult's law at all temperature as well as the concentration is called as Raoult's law. Sir, what is meant by obeys Raoult's law? Means experimentally calculated pressure from Raoult's law calculated pressure should be same. That is only called as obeying Raoult's law. Right, next. Before mixing attraction forces, after mixing attraction forces should be same. Next characteristic feature. Before mixing volume, before mixing a total volume, after mixing a volume should be same. And next, delta H mixture 0. Before mixing energy, after mixing energy also should be same. Because before mixing bonds are breaking, need energy. After mixing, after formation of bond, energy releasing, here required energy, released energy should be same. These are the characteristic features of ideal solutions. And now we have to plot a graph for ideal solution. Ideal solution graph is already familiar to you. Let's discuss ideal solution graph and then we'll stop our today's class. In our NCERT book, instead of component 1, 1 or 2, 2, he has shown like A, B, like AB, like that also he has shown. It is a solution, it is a B solution, it is a AB solution, it doesn't matter. Any type we can write. 1, 1, 1, 1, 1 we can write. 1, 1, 2, 2, 1, 2 or AA, BB, AB, any type you can write, there is no any problem. Now just we'll see graph of ideal solution. Then we'll stop our today's class, right? Yeah, same. Here x like 1, 0. x1 is equal to 1, x2 equal to 0. Here I am taking a mole fraction. Here I have taken a vapor pressure. Then here x1 equal to 0, x2 equal to 1. I have taken same type of plot. Then again, here only component 1 is there. Component 1 partial pressure P1 naught. Here only component 2 is there. Component partial pressure P2 naught. Say component 2 vapor pressure is somewhat higher. Then what happened? What happened means here only component 1 is there. From left to right, what happened? Component 1 becomes 0. That's why here pressure also is getting a 0. It is a P1. Next, here only component 2 is there. That's why its pressure is P2. When we are coming from right to left, component 2 becomes 0. That's why its pressure also becoming a 0. It is a P2 and it is a total pressure. P total is equals to P1 plus P2. Of course, this is only ideal solution graph. Ideal solution graph which obeys Raoult's law at all concentration as well as temperature. And the last ideal solution, some examples are there. They are ideal solution examples like benzene plus a toluene. Generally, which we are considering as examples means their size should be almost same. Of course, I am not telling 100% same, almost similar size examples we are taking. Benzene plus toluene, chlorobenzene, bromobenzene, chlorobenzene, bromobenzene, like that. Chlorobenzene plus bromobenzene. Like that. Many examples are there, many examples given in your printed notes. You just by heart all the examples of ideal solutions. Okay, right? Then now we'll stop our today's class and in tomorrow next class we'll continue with non-ideal solutions. Okay, thank you for watching. Bye.